Hello everyone, and welcome back to another quiz tutorial. So in this tutorial, or quiz, whatever you want to call it, we're going to be talking about quiz number 3, which has to do with linear independence or linearly dependence. And what this is this kind of helps us define basis sets. And basis sets will become very important down the road as they are used for transformations, stuff like that. Very important topic, but right now we're just going to go to a nice simple question, which is a set of vectors linearly dependent or linearly independent? And this is such a great question because it's a perfect little midterm question. As you guys will see, the midterm questions, they're very much like these quizzes where they're short, sweet, and to the point. So how much sweeter does it get than which one of these set of vectors is linearly independent? Stuff like that. So it's a great midterm question. So hopefully we can go through it and it makes sense to you guys. So before we get into the examples, let's just cover a little bit of theory. So the theory states that a set of vectors is linearly independent if none of the vectors in the set can be expressed as a linear combination of the other vectors in the set. So this may sound very confusing. I know myself, I can never interpret math from words. I need an actual example. So let's say that we have a set of vectors v, which are v1, v2, and v3. So what I'm going to do is I'm going to express these vectors as a linear combination of each other in the following equation. So some factor alpha times v1 plus another factor alpha times v2 plus a third alpha times v3 should give us the zero vector. And in this case, we usually know v1, v2, and v3, and the zero vector is, well, the zero vector. You guys should hopefully know that by this point. So what we're going to go and do in this is we're going to solve for alphas, all three of those alphas. And we're going to have two possible scenarios. The first one is alpha 1 is equal to alpha 2, and which is equal to alpha 3. So basically all your alphas are 0. This is linearly independent. So this means that these vectors can actually form a basis set if they're linearly independent. The second case is alpha 1 or alpha 2 or alpha 3 do not equal 0. Basically there's a solution to that problem, to that statement above. And if this is the case, what this means is that set of vectors is linearly dependent. So that's all we're going to do in these questions, are solve for the alphas, and we're going to say, okay, well, if all of our alphas are 0, it's linearly independent. If one of our alphas is not 0, well, that means that there's a solution, so therefore the equation is linearly dependent. It's as simple as that. So to help illustrate that, let's jump into the examples. All right, so the quiz itself is going to be 2 questions. First question is a little bit longer than the second question, but we'll get through it and it won't be that bad. So question 1, very, very simple question. It says, are the following sets linearly dependent or are they linearly independent? So again, great midterm question because it's so short and easy to the point. For linearly dependent, I'm going to mark that as LD. So if you see me put LD, that means linearly dependent. Linearly independent, I'm going to put LI, something like that. So if we look at A, it says that B is equal to the set XY. So this does not mean B is 2 dimensions. A lot of people see XY and think, oh, that just means that this is in 2 dimensions. That's not what this means. What this means is the set of B consists of 2 vectors, X and Y. And then we're given X and we're given Y right here. So just like we talked about in theory, the best way to do that is we're going to express this as a linear combination. So what we're going to have is we're going to have alpha 1 times x, which we know is 1 and then 0, plus alpha 2, and then from here we have y, which is 5 and then 0, and then we're going to make this equal to the 0 vector. So since the vectors are 2 numbers long, the 0 vector is going to be 2 numbers long, or basically nice and easy. So from here we can kind of expand this out, and what we're going to do is we're going to get 2 equations. We're going to get alpha 1 times 1 plus alpha 2 times 5 is equal to 0. So what I did there is I took alpha 1, multiplied it by the first number in that vector, plus alpha 2 times the first number in the second vector is equal to the top number of the 0 vector. And then my second equation is the same, except now I do the bottom number. So I get alpha 1 times 0 plus alpha 2, and then this one's also times 0 is equal to 0. So in this case, well, we can kind of look and say, okay, equation 1 is I'm sorry, equation 2 is kind of crap. So what we can do is say, this doesn't tell us anything because we're just multiplying a bunch of things by 0. And then the second one simplifies, and I guess we'll do the simplification in blue. So if I were to simplify this right here, what we get is we get alpha 1 plus 5 alpha 2 is equal to 0. And this is all we have. And if we look at this equation, and that's the only equation we have, well, there's going to be an infinite number of solutions. So therefore, alpha 1 and alpha 2 do not equal 0. They can equal an infinite amount of solutions. So since there's an infinite amount of solutions, this is linearly dependent. So I'm just going to put right here. So that equation, there's infinite. Oh, not a bad sign. Infinite solutions. Usually my infinity signs look like complete garbage. So infinite solutions. Therefore, in this case, this is linearly dependent. So LD, again, stands for linearly dependent. So we move on to the second question here. It's the same thing. We have a set B. Oh, sorry, guys. I'm just trying to figure out. I wanted the green. So it's the same thing where B is composed of 2 vectors, except this time the Y vector is a little bit different. So the same thing as before. We have alpha 1 times 1, 0 plus alpha 2. But this time, instead of 5, 0, it's 0, 5. And this is going to be equal to the 0 vector. So 0, 0, like that. So what we're going to do, just to make our lives a little bit easier, is we're going to slowly simplify this equation. So we have alpha 1 times 1 plus alpha 2 times 0 is equal to 0. So this is equation 1. And from here, we can actually see, well, since alpha 2 is times by 0, this kind of goes away. And we get alpha 1 is equal to 0. So from here, we get alpha 1 is equal to 0. So that's kind of a good start, because remember, to be linearly independent, we want both of those equal to 0. So the second equation, we got alpha 1, but this time this is times 0, plus alpha 2. And this time it's times by 5. And this is equal to 0. So the same process as before, alpha 1 times 0, well, this is going to be 0, so we can get rid of that. And what we end up with is 5 alpha 2 is equal to 0. So in order for that to be true, alpha 2 must also equal 0. And then since alpha 2, or I guess alpha 1, is equal to alpha 2, which is equal to 0, so all of our alphas are in that term, all the alphas in the equation are equal to 0, this means that this equation is linearly independent. So that's why I have Li. And sorry, that's not a good horizontal line. So Li, linearly independent, because both of our alphas are equal to 0. So now things get a little bit different, but there's kind of a trick to this one. I really like this one. So the first thing is B now is a set of 3 vectors, x, y, and z. So x, y, and z, those are vectors. It's not dimensions. At first you look at the x, y, z, oh, we're talking about 3D now. No, that's not quite the case. We're still just talking about whatever the dimension of the vectors are. And all we're saying now is that instead of being composed of 2 vectors, the set B now is composed of 3 vectors. So we have x, which is 1, 0, y, which is 0, 5. So those are the exact same as before. But now we have this third vector, z, which is 0, 0. And I like this one because this one could be a really good, let's say a midterm trick, something like that. So right away, I can say that this right here, the set of vectors, is going to be linearly dependent, LD. And the reason why is because it has a 0 vector. So 0 vector, I'll just write that down. Any set of vectors that contains the 0 vector is going to be linearly dependent. So that's kind of a little bit of a trick, help you save some time, maybe some midterm time, something like that. So since we see that z is 0, 0, we can conclude right away this is linearly dependent. So now we move on. Okay, same scenario, except all we did is we changed z, so now that's 4, 3. It's not 0, 0, 0. Sorry, it's not 0, 0. Well, now we can write down our equation. So we'll have alpha 1 times x, which is 1, 0. And we have plus alpha 2 times y, so in this case 0, 5. So this is starting to look very, very familiar. But now we have that plus alpha 3. So if there's another vector, we just add another alpha, times 4, 3. And this should always still be equal to 0, because remember, we're solving for the alphas. We're not solving what this is equal to. So in this case, what we're going to do is we're going to write down the equation. So we're going to have alpha 1 times 1 plus alpha 2 times 0 plus alpha 3 times 4 is equal to 0. And then in the second equation, we're going to have alpha 1 times 0 plus alpha 2 times 5, and then plus alpha 3 times 3 is equal to 0. So right away, you guys should kind of have something clicking in your head that says, okay, well, I have 3 unknowns, but only 2 equations. And if this is the case and it's an overconstrained system, what this means is that there's going to be an infinite number of solutions for this case again. So for this case, we have infinite solutions. See, this is my normal infinity signs. You see how much more they look like garbage compared to the last one? So infinite solutions, therefore this is also going to be linearly dependent. So because our alphas are not all equal to 0, we have a linearly dependent solution. So moving on to E, things start to get a little bit, not trickier, but a little bit more interesting. And the reason why I say that is because if we look at the vectors now, they have 3 components. They're not just 2 components like the last ones. However, the same procedure still applies. So what we're going to do is we're going to write down the linear combination. So we're going to have alpha 1, and instead of 2 components, we have 3 now. So we're going to have 1, 0, 0 plus alpha 2 times y, and we see that y is 0, 5, 0, plus z, so plus alpha 3, and then z is 4, 3, 0, and this is going to be equal, of course, to the 0 vector, so 0, 0, 0. And if you guys look, you guys can kind of tell right away that, hey, something's a little bit weird, because if we simplify this, well, we get alpha 1 times 1 plus alpha 2 times 0 plus alpha 3 times 4 is equal to 0. So far, doesn't seem like there's a problem. Moving on to the next equation, alpha 1 times 0 plus alpha 2 times 5 plus alpha 3 times 3 is equal to 0. So this is actually interesting, because if we look above and we kind of compare it to the last one, these are the exact same equations that we had before. And remember, we couldn't solve those 2 equations before because we had 3 unknowns. But now we actually have that third equation. But if we look and we expand it out, we got alpha 1 times 0 plus alpha 2 times 0 plus alpha 3 times 0 is equal to 0. So we look at this, even though we have that third equation, this third equation is useless. So in this case, which is kind of funny, let's go to pink. This equation means nothing. We're basically left with 2 equations, but 3 unknowns. So it's the same as before, where we have infinite solutions. And if we have infinite solutions, therefore our set is linearly dependent. All right, so moving on to part B. So you guys can see how fast this goes. Once you get the hang of it, it goes by really, really fast. And as we can see from part B, things start to look a little bit different. So expanding it out, we got alpha 1, and then it's going to be times x, which is 1, 0, 0. I'm doing it in pink, even though I've been doing it in green. So maybe this will hint you guys that this could be a special case. Not a special case, but maybe we'll finally get linearly independent. As you guys see, we haven't had a lot of it. So after expanding it out, we get this is equal to 0, 0, 0. And I know I'm making this small, and the only reason why is I'm doing it fast because we're going to write all these out. So equation 1, what we're going to have is alpha 1 times 1 plus alpha 2 times 0 plus alpha 3 times 4 is equal to 0. So there's equation 1, and we can't solve anything from that yet. Equation 2, we got alpha 1 times 0 plus alpha 2 times 5 plus alpha 3 times 0. And if we look at this one, we have two cases where the alphas are times 0. So alpha 1 times 0 is nothing. Alpha 3 times 0 is nothing. So we're left with 5 alpha 2 times 0 is 0. So from here, we can see really quick that alpha 2 is equal to 0. I got this kind of like neon thing going on, starting to look like my computer. All right, so finally, third equation. Oops, I'll really start messing up. Got to go back to that neon pink. All right, so we got alpha 1 times 0 plus alpha 2 times 0 plus alpha 3, but this time it's times by 3 is equal to 0. So this is just like the second equation where alpha 1 times 0, well, that's going to be 0. Alpha 2 times 0, that's also 0. So we're left with 3 alpha 3 is equal to 0. Well, the only way that holds true is if alpha 3 is equal to 0. And then now if we go back up to the first equation, well, alpha 2 times 0, that's going to be 0. We're left with alpha 3 times 4, but we already know that alpha 3 is 0, so this is going to be 0. So now if we look, we have alpha 1 is equal to 0. So alpha 1 is equal to 0. So now that we solve for the three alphas, we can conclude that alpha 1 is equal to alpha 2, which is equal to alpha 3, which is all equal to 0. And since all three of our alphas are 0, this can be linearly independent. So if we look through all these, we only had two cases where things are linearly independent. It's much more likely that things are going to be linearly dependent. But be aware on an exam because it can get a little tricky. Well, it can get a lot tricky really fast. All right, so the second question is even nicer. It says the set B, which composed of two vectors, E1 and E2, where E1 is 1, 1 and E2 is 0, 1, is linearly independent. Therefore, it can form a basis set in R2, so in 2 dimensions. In this case, the vector u, which is 3, 4, can be uniquely expressed in terms of the basis vectors u is equal to u1, e1 plus u2, e2. And it wants us to determine the values of u1 and u2. So these u1 and u2 right here, these are going to be scalar values. These are not going to be actual vectors. So the best way to do this is just to plug everything into the nice equation it gives you. So it already gives you that u is a linear combination of e1 and e2. So we have u1, e1 plus u2, e2. So what we do from there is, well, we know u and we know e1 and e2. So let's just sub in values and see what happens. So we know that u is given. It's given right here is u is equal to 3, 4. So right here we're going to have 3, 4, and this is going to be equal to u1. We don't know u1 yet, so I'm just going to leave it at that, times e1, and e1's a vector. So if we look at the top, we're given that e1 is equal to 1, 1. So I'm going to come down here. I'm just going to put, okay, u1 times 1, 1. And then plus u2. So u2 is another thing that we're trying to solve for, and this is multiplied by vector e2. So if we look, e2 right here is equal to 0, 1. So I come down here, I have 0, 1. So just like that. So what we can do is, just like before, we can expand this out to get two equations. So what we have in the first equation, looking at the terms on top, is we have 3 is equal to u1 times 1 plus u2 times 0. And now equation 2, so I'm going to put this as equation 1. And then equation 2, we have 4 is equal to u1 times 1 plus u2 times 1. I'm going to call this equation 2. So if we look at these two equations, and I'm going to switch to green here really quick. If we look at equation 2, well, we have u1 and u2. So we have two unknowns, one equation. We can't really solve for anything right there. We can manipulate it to make one variable in terms of the other, but no, I prefer a quick solution. I'm lazy. You guys know I'm lazy. So if we look at equation 1, so equation 1, what we see really quickly is that u2 is multiplied by 0. So theoretically, this goes away. And from there, we have 3 is equal to u1. And well, it's times by 1, but it's the same thing. So just right then and there, we solved for u1. It's equal to 3. And then we can go to equation 2 and substitute this value in. And what we have is 4 is equal to u1 times 1, but we know u1 is 3. And then plus u2 times 1, so u2. So plus u2. And then from here, well, this is as simple algebra as it gets. We can conclude that u2 is equal to 1. So, nice simple problem. As you guys can see, it's a great midterm question because you guys can solve it right away and really fast, and it doesn't take too much work. It can be a little bit trickier in some cases, but I'm sure you guys will be just fine. So I'm just going to conclude really quick that u1 is equal to 3. And that u2 is equal to 1. I'm so used to Eng 130 where I have to tell the kids all the time, oh, make sure you box your answers, stuff like that. So I better get in the hang of that too, or else I'd be quite the hypocrite. So yeah, that's quiz number 3. As you guys can see, not bad, short and sweet. But I must warn you, when we're starting to talk about basis and stuff like that, it's going to get a little bit more complicated. So it's good to know these nice, easy ones because when it comes down to the midterm, it's all about getting those nice, easy marks. The hard question, who cares? You guys can pass just on easy marks. So that concludes quiz number 3. Thank you guys all so much for listening, and I'll see you guys in quiz number 4.